All right, so in this particular video, I have a couple of different torque problems for you to keep up here. The first one is this one. It says the uniform 8.4 kilogram spherical shell. It has a diameter of 50 centimeters and it has four small 2 kilogram masses attached to the outer edge. So essentially, if you look at the diagram here, here's the spherical shell, aka hollow sphere. It has 4 point masses that's attached to the outer edges. It seems like it's pretty symmetrical. And then the axis spins right through the dashed line there. And it wants us to find out how much torque is needed to reduce the speed from 75 revs per minute to 50 revs per minute in a time of 30 seconds. All right, so we need to pause and read that again. So I'm just going to go ahead and point out a couple of things here that's important. I think as you practice these problems, learn to identify variables given, and then hopefully extract information correctly. The distance given here is the diameter, and the diameter is given as 50 centimeters. So right away, the unit centimeters should be converted to meters. This way you don't goof on your values at the very end. The other thing is the diameter is given, right? So 50 centimeters is not the radius, it's the diameter. So I'm just going to go ahead and draw my radius from the axis of rotation there to the outer edge. It's going to be 25 centimeters. That's half of 50. But don't forget to convert 25 centimeters to meters. 25 centimeters is 0.25 meters because you would take this and divide it by 100 because it takes 100 centimeters to make a meter. Okay, so if your conversion is solid, accept that. If not, I would say practice conversion. So you should get 0.25 meters as the radius. All right, other than that, the other thing I'd like to point out here is that the units for the English speed here is given in revs per minute, and you need this to be in rads per second. So I'm just going to go ahead and crack out the conversions here for revs per minute. The first one is 75 revs per minute. For every one revolution, there's 2 pi rad. And then for every minute, there are 60 seconds. So if you do this correctly, the unit revs will cancel out top and bottom. And then the minute will also cancel out. And that'll leave you just with rad per second. So all this on your calculator should give you a value of about 7.854 rads per second. And I'm also going to convert 50 revs per minute as well, just to get the conversion out of the way. Again, following the same procedure, 50 revs per minute is equivalent to 5.236 rads per second. Now that I have everything in rads per second, and don't forget, make sure you convert centimeters to meters, I'm just going to go ahead and apply physics here. Well, the question essentially asks for the frictional torque. So in this particular problem, I'm just going to set up net torque equals I alpha. The only force acting on this particular system, as indicated, is some sort of frictional torque that's going to cause the system to slow down its angular speed. So here, I'm just going to expand my net torque to just really the torque due to friction. It is the only torque presented in this particular problem. The moment of inertia of the system here. I expanded I to include the spherical shell, which is a hollow shell. Okay, and the hollow shell has a moment of inertia of 2/3 mr square. And then here I have 2 mr square term highlighted in blue. Why the problem states that there are 4 2 kilogram masses. 2 of the masses lies through the axis of rotation, which implies that there's no r. So while there is an m, there's no r to multiply by because it runs right through the axis of rotation. So the only 2 point masses that has some sort of moment of inertia here are the left one and the right one that has a distance away from the axis of rotation. So make sure you understand how to find I, otherwise you might sit there and find 4 of them when you really only need to find 2 of them. Okay, and then I expanded alpha into its definition here is final angular velocity minus initial angular velocity divided by the change in time. So here we're given a bunch of information already, right? I'm just going to go ahead and plug in m of the sphere, which is 8.4 kilogram. That's given. Once again, the radius of the sphere is 0.25 meters. Make sure you convert, and then don't forget to square that. And then here I highlight the 2 just because I have an mr square plus an mr square, which is essentially just 2 mr square, but what m is the mass of the object that's attached to the outside. Okay, that's it. And then the how far is it away from the axis of rotation is 0.25 meters away from the axis of rotation. And then the final angular velocity, I already calculated it, which is 5.236, and I want to subtract it from the initial angular velocity there, which is 7.854 divided by a time of 30 seconds, which is given. So if you do all this on your calculator, to clean up a little bit, the first term here, the 2/3 0.84 0.25 square. That's going to leave you with about 0.35. And then 2 times 2 times 0.25 square is going to leave you with 0.25. And then the angular acceleration here, if you do it properly, is going to give you negative 0.0873 rads per second square. That's assuming that it's moving in the positive direction to start with. However, if you go ahead and clean this up, it really, again, when the physics done here, all this is just calculator work. You'll get a frictional torque of about 0.5238 Newton times meter. Okay. Now, in my answer here, though, I have plus or minus. Well, I don't know if it's plus or minus, only because the problem states that the angular speed was given. So I don't know initially whether the system is moving in the clockwise direction or counterclockwise. So speed is a scalar, so it doesn't really indicate the directions. Okay, so I'm just going to be safe and just going to put plus or minus for torque, because if it was initially moving in the counterclockwise direction, then the torque would be in the clockwise direction and vice versa. So, but again, unless otherwise stated, I would just assume that it's moving in the positive counterclockwise direction, and then your torque here would just be negative if you follow my work. But I put that plus or minus there once again just to be safe in case the problem gets technical on the direction of the movement. All right, so that's that. Let's go ahead and do the next one here. Here you have a thin uniform rod. The bar itself has a mass of 3.8 kilogram, and then you have two spherical objects here, balls on the outside of each of these ends that has a mass of 2.5. And it tells you essentially the right one essentially falls off. Okay, all of a sudden it falls off, and it wants us to find A, B, and C. So if you need to pause, read A, B, and C. All right, let's go and do it. Part A wants you to find the angular acceleration of the bar just after the ball on the right side falls off. So here I'm just going to go ahead and clean this diagram, and I'm just going to delete or erase here the ball on the right because it's no longer in play. So essentially the ball on the left is going to cause some sort of rotation because it's now offset, right? The axle is here through the center, which makes it nice for this one. So I'm just going to go ahead and draw out my f of g here. My f of g is just mass of the ball times g. And then, well, the rod also has a weight, right? And the weight of the rod is drawn through the center of the rod. So here I have m ball times g, m bar times g. But once again, the problem for part A asks you to find angular acceleration. So I'm going to go ahead and set up my net torque. But to find net torque, though, I need my forces and how far is it away from the axis of rotation. So here, I do want to point out that 80 centimeters given. Keep in mind, centimeters not appropriate. You need to convert 80 centimeters to meters, which is 0.8 meters in this one. All right. So I'm just going to set up net torque here. Net torque generically is equal to I alpha. Now, why am I using this and not F times R? Well, the question asks you to find angular acceleration. So why not use the torque statement that has the variable that you're interested in, right? So I'm just going to say net torque is equal to moment of inertia times the angular acceleration. Well, here I can find net torque super duper easy. Net torque is just F times R. But if you look at this particular diagram on the bottom here, right? Using common sense, the way the ball on the left side is going to cause the system to rotate. Okay, so I'm just going to go ahead and expand that. Well, my f of g, which f of g is it? Why in the diagram here I have fg for the ball and I have fg for the bar. I actually need to use fg the ball because it's a distance of 40 centimeters away from the axis of rotation. All right. Well, so here in my work, I have m ball times g, that's f of g the ball. How far is it from the axis of rotation? It's just the whole entire length divided by 2, because the whole length is given as 80 centimeters. So half of that would be 40 centimeters, or 0.4 meters if you've already converted. And then on the right side, well, what's the moment of inertia? Well, this is a ball and a rod, right? The rod here is being spun at the center. So the moment of inertia for a rod through the center is 112 ml square. Here I indicated m bar for you. Again, here you have a couple of masses, so make sure you plug in values correctly. Well, L here is already given. And on the right side, I have m ball times r square generically. But what is my r? My r is just going to be half of the length of the rod, which is L divided by 2. And I'm going to square that. But once again, really you already know this answer, or the value here. L over 2 is just 0.4 meters, okay? And then the only thing I don't know here really is just alpha. So I'm just going to go ahead and plug all my values in. I did this symbol here for you. So why you can draw f of g for the bar, it doesn't generate any torque because there's no r, right? this particular f of g for the bar runs through the axis of rotation. So to generate torque, you need an f and an r that's a distance away. So why here you have an f of g for the bar, there is no r because it runs right through the axis of rotation. So this weight for the bar contributes no torque for this particular problem. All right. So I'm just gonna go ahead and cross that out. So the only force I need is really mg for the ball, and then how far is it from the axis of rotation. So as I indicated there, the mass of the ball is 2.5 kilograms, which is given. G is 9.8, and then how far is it from the axis of rotation? It's 0.4 meters because it's half of the length of the rod given. And here the mass of the bar on the right side is 3.8. L, you need the whole entire length of L here, which is 0.8 meters, and don't forget to square that. And then on the right side, the second term here is m ball, which is 2.5, and it's a distance of L over 2, which is 0.4 meters. Again, the whole length is 0.8, so half of it would just be 0.4. We're going to square that. And then really here's just all calculator work, okay? Because the only thing unknown is your alpha. On the left side, if you reduce it, you get 9.8. On the right side here, these two terms, I just cleaned up one by one. If you do 112 times 3.8 times 0.8 square, you'll get 0.2027. And then if you multiply 2.5 times 0.4 square, you'll get 0.4. And then all that on the outside is your alpha. So make sure you use parentheses there to differentiate your quantities that you need to sum up. Once you do that, 0.2027 plus 0.4 is 0.607. So to get alpha by itself, I would just divide by that quantity. On the left side, it's just 9.8, so it'd be 9.8 divided by 0.6027. And if you do that correctly, you'll get a value of 16.26 rads per second square. So here I put a plus sign because by convention, going counterclockwise is positive. So if you visualize this, if you take the ball, or if the ball on the right side drop, on the object or the rod ball system here will swing in the counterclockwise direction. And we'll take the counterclockwise direction to be positive. And that's it. So the direction here is positive, and then the magnitude is 16.26. The unit is rads per second square because we're finding angular acceleration. All right, let's go ahead and do part B. All right, so part B says, will the angular acceleration remain constant as the bar continues to swing? If not, will it increase or decrease? Well, how do you know that? Well, it's super easy to do. I'm just going to go ahead and set up torque. Torque equals I alpha, right? The question asks you for alpha. Once again, is alpha constant? So I'm just going to go ahead and I say alpha by divided both side by I. But as you can see here, if you kept up with the previous work in part A, well, the f of g here is f of g the ball, right? Well, how far is it? It's some distance away from the axis of rotation. So in this particular image on the left, it's a distance L over 2. Keep in mind the word perpendicular. Well, what's I on the bottom? The moment inertia here for the system stays constant because you have the rod and the ball. And the rod's axis of rotation is through the center, and the ball is glued to the outer edge, which means it's constant. All right, so I'm just going to draw you a second, rod here, just to help you visualize as it rotates, right? The ball's still on the left end of the string. The weight of the ball is still pointing down the page, right? F of G always directs down the page. So here, this is the length of L over 2, which it hasn't changed. I'm referencing the center of the rod as the axis of rotation. And then here, I'm just going to go ahead and call this some theta. The dashed line is what you need, right? Because when you do torque, you have to think perpendicular. Well, your F of G here lies in the y-axis. L over 2 is not perpendicular to that. You need the perpendicular component, your moment of arm. So here, I just put theta here. Again, it doesn't really matter where you put theta. The point is that you cannot use L over 2 because it's not perpendicular. So you have to use L over 2 in this case, cosine theta. It's cosine because the angle I place here touches the horizontal axis. So the dashed line is what you need because it's perpendicular to F of G. That's on my page here. Well, as you can see, I can just go ahead and box this up. Well, F of G is just mass times gravity. Well, that hasn't changed because the mass of the ball hasn't changed, right? G hasn't changed. The moment inertia of the system hasn't changed because you have a rod that's spinning around an axis of rotation through the center, and the ball is still glued to the end. The only thing that's different here is the R, right? In this particular function for torque, R is defined as the distance, the moment of arm from the center, right, from the axis of rotation to where the force is being placed, but it has to be perpendicular to it. So here, I'm just going to box up F of G and I. I'm just going to call that some sort of constant because these two values don't change. F of G doesn't change, I doesn't change, so I can pull it out. It's just some number to me. But what I did highlight here is r, because r is not just the radius. Once again, it's the distance that's perpendicular to the force that's being applied that's generating some sort of torque. So here r varies. R in this particular rotation here is L over 2 cosine of theta, right? Because L over 2 cosine of theta is perpendicular to f of g. Well, as the rod swings, theta changes, and I think that's a common sense thing, right? When it's perfectly horizontal, the angle is 0, and as it rotates, the angle changes. Well, as the angle changes, alpha has to change, so it can't be constant. So here I just circle alpha and I say it's not constant. Alpha depends on theta as an object is allowed to fall and swing on some sort of axis. So here I'm just going to say a decrease, because if you punch in theta and as theta in this particular problem increases to, let's say for example, if the rod, once the rod gets all the way to the vertical, well, it has fallen 90 degrees. So if you punch in cosine 90 degrees, alpha here is going to be 0. Okay, so it decreases, so it's going to start some maximum value and it's going to approach 0. So the point is that it's not constant and it actually changes. Alright, so it decreases because cosine of theta decreases as it swings down. If you don't believe me, just punch in your calculator. Alright, let's do C. So C here said all of a sudden, once again, the ball on the right falls off, still the same scenario, and it wants us to find the angular velocity of the bar just when it's through this vertical position. So here is the initial diagram. I just drew an additional bar here in the vertical position here for you. So well, how do you find the angular velocity of the system, right? This system move S1, right? The ball is glued to the rod. So however fast the rod is moving, the ball is also going to be moving with it at the same angular speed or angular velocity if you care for direction. So here I'm just going to use conservation energy. Well, what is going to cause this particular system to start moving? And that is the weight of the ball, right? Because the axis rotation for this particular problem is through the center of the rod. So the f of g here is not offset. So at the weight of the rod will not cause it to rotate, because the f of g once again lies through the axis of rotation, so it doesn't generate any torque. It's this weight on the left side due to the mass of the ball that's going to cause it to rotate. So here, I'm just going to say that the ball initially has some sort of gravitational potential energy because it's going to fall. So it's going to start high and it's going to fall low. So if you look at my diagram, the ball is over here. As it swings down, it has dropped a distance of L over 2, which is half of the length of the rod, right? So where that potential energy go? Well, it's going to get converted to kinetic energy because it wasn't rotating, and all of a sudden now it's rotating. So all that PE will be converted to KE. There is no KE linear for this particular problem because this particular system is fixed at the center of this rod here. That's the axis of rotation. All right. So other than that, I'm just gonna go ahead and plug in Chuck. I'm just gonna go ahead and move the 2 to the top left, and I'm gonna divide both sides by I total to get omega squared by itself, because part C wants us to find what is this? Oh, the angular velocity. All right. So the mass of the ball is 2.5, g is 9.8. The initial height here is 0.4. Keep in mind, again, as the ball swings downward, it only drops a distance of L over 2. So it's a common error to put L. Not for this particular problem, because the ball is placed at the midway point and the axis is through the midway point. So make sure you pay attention to how far the object actually physically falls in different types of scenarios. All right, other than that, I total I already found in the first part. So if you need to rewind the video, the 0.6027 came from doing 112 ml square plus mr square. Okay, and then once I'm just gonna clean this up, all the stuff on the left side, if you do any calculator, we reduce down to 32.52, and that's omega square. But we still need to square root both sides just to get omega by itself. So the square root of 32.52 is going to give you roughly 5.7 rads per second. And here I put positive once again, just because we take the direction of counterclockwise to be positive. And that's it. It says angular velocity, so make sure you include direction, or you can put 5.7 rads per second counterclockwise. It is entirely up to you. All right, I hope that helps. Stay nerdy, don't be wired.